let's talk about the inner product on the space of symmetric functions. And before this, we'll talk about a very interesting identity called the Cauchy identity. Okay, now this is actually something that we have seen already before in various contexts, but let's put them all together. So recall the HT that we talked about. Okay, so this is the generating function, generating series for the complete symmetric functions. And we could also, just as we did for the elementary symmetric functions, we could replace t by yj, look at the product of all the hyj's. Okay, so what would that give us? Well, just as this gave us summation hn t power n, if you recall the way the argument worked in the case of the elementary symmetric functions, the same sort of thing works here as well. This says that this is nothing but, well, you have to look at all partitions. So look at lambda belonging to par, which means set of all partitions of all numbers 0 onwards. And for each such partition, the coefficient of m lambda of y, okay, turns out to be exactly h lambda of x. Okay, so this is what that earlier calculation. So we have already done one such calculation, but with the e's in place of the h's. Okay, so here's the corresponding version with the h's. So let's just rewrite this. What's the left hand side? This is actually a product over i's as well as j's running from 1 to infinity of 1 minus xi yj inverse. Okay, so this is the identity. This is the first version, if you wish, of the Cauchy identity. So let's just this identity here is well, one of the versions of the Cauchy identity. So let's just call this 1. Now let's look at the left hand side of this identity, the 1 minus xi yj inverse, and try to work with it in slightly different ways. Okay, so here's another thing that one can do with it. So you recall we just talked about the power sum symmetric functions, and we can try and rewrite this in terms of the power sum symmetric functions. Okay, so how would we do this? Well, you would take log. So recall somehow log was the right thing to do in the case of the power sum symmetric function. So let me just see what happens by taking log first. Xj inverse becomes minus log minus summation ij log of 1 minus xi j. And if you see what this is, now you write out the expansion of log, this just becomes there's a minus of a minus, so there's plus, so it's a sum over all ij, it's a sum over all n from 1 to infinity of xi yj power n divided by n. So this is just the power series for logarithm with xi yj in place of t. Log of 1 minus log 1 minus t would just be summation t power n over n. Okay, but what is this really? If you see, how do we write this? Well, we can sum over n on the outside, and on the inside it's just sums over all possible xi yj whole power n. So this actually factors as summation xi power n summation yj power n. In other words, I can write it as pn of x times pn of y. Okay, and there's still a factor of n on the bottom. So that's my that's a result of taking log, and therefore we just exponentiate, right? So therefore the left hand side of the Cauchy identity, which is 1 minus xi yj inverse for all i's and j's going from 1 to infinity, is just the exponential of this guy. Okay, and this sort of computation is what we did when we calculated the expression for h in terms of p. Okay, so if you sort of look back on on what that gives. If you recall, what we got there was, this is now running over all partitions. There we had fixed a particular d and we were looking at the coefficient of a certain t power d, but now here I'm just going to look at all of them. So here's what happens. Okay, so it's the same computation as before. It says that this sum is now, when you take the exponential, I get that term z lambda. Okay, and you recall the definition of z lambda, etc. But my point here is really to say the following, that here is another way of rewriting the same left hand side, the same product, but now in terms of the power sum symmetric functions. Okay, it's p lambda x into p lambda y by z lambda. The earlier expression right here was the same infinite product is a sum of h lambda times m lambda. Okay, h lambda in terms of x, m lambda in terms of y. Here it is p lambda in terms of x and again p lambda, but then normalized p lambda divided by z lambda in the y variables. So here's sort of version 2, if you wish, of the Cauchy identity. Here's the second Cauchy identity. So the product, the infinite product on the left hand side is the Cauchy product that we are trying to understand. Okay, finally let's do one more version of this, which is the same product 1 minus xi yj, but now we'll sort of interpret it differently. So product 1 minus xi yj inverse over all i's and j's is, well, I can think of it as 1 plus xi yj plus xi yj the whole square plus xi yj the whole cubed and so on. Okay, just the infinite sum, but it's a product of all such terms. So what is a typical term when you expand this product out? Well, it looks like this, right? So from each ijth term, I just have to pick out some number. So it's xi yj to some power. So I pick out some aij. Okay, from the ijth term, and this is now going to be a sum of all such products. So this is a product all ij going from 1 to infinity, and the sum was over all possible such aij's, all possible choices. Okay, now what is this matrix? I mean, what is this collection tuple aij? Well, I can think of it as a matrix. It's an infinite cross infinite matrix. So let's call it A. I will just arrange the aij's in the form of a matrix. Now, when I do that, what am I talking about here? Well, look at how the ijth entry works. It's xi yj power aij, right? So this I can think of as follows. I can say, well, aij is a matrix, so let me sum over all infinity cross infinity matrices, and the power that I pick for the x and the y, the power that I finally get is the following. Right? What's the power of xi? It is, the same xi will occur for all, all the different j's in some sense. So to get a particular xi, I have to look at the corresponding, the ith row sum. So this is a product over I, xi power ith row sum of this matrix A. Okay, similarly, product over j, yj power jth column sum of A. Okay, so by the way, this matrix that I am talking about here only has finitely many non-zero entries. Right? So when I do this sort of infinite product, what it means is that from almost all terms, I have to pick this one. Okay, it's only from finitely many terms am I allowed to pick things other than one. Okay, only then the product actually makes sense. Okay, so this is this is the sort of term that you get. So I'm just going to rewrite it as follows. It's a sum over all infinity cross infinity matrices with finitely many non-zero entries of x. Remember, x is the shorthand for the infinitely many variables, the tuple x to the row sum of A, y to the column sum of A. Okay, so that's the same thing, just shorthand for this. Okay, and now we sort of remember what this means. This, if you recall, is just the RSK correspondence in some sense, that non-negative integer matrices. So observe that the Aij's are all non-negative integers, right? So here is a non-negative integer matrix A, and what I'm doing here is summing over all possible non-negative integer matrices of a particular monomial, which is x power row sum of A, y power column sum of A. And the RSK correspondence tells me that non-negative integer matrices are actually in one-to-one correspondence with pairs of semi-standard Young tableau of the same shape, right? So I take PQ, semi-standard tableau of the same shape. Shape P equals shape Q. Okay, and let's give that shape a name. Let's call it lambda. Now I'll sum over lambda, so over all partitions. So lambda now runs over all partitions. Okay, so for each lambda, I take all semi-standard tableau of shape lambda. And then what else do I know? I know that the row sums of A are exactly the types of, that's the type of P. The column sum gives me the type of the semi-standard tableau Q. Okay. Now, what does this mean? This tells me that this sum splits into two pieces. The sum over all partitions lambda of x power type P. I can just sum over P alone. Okay. So P is a semi-standard Young tableau of shape lambda, x power type of P times sum over all Q semi-standard of shape lambda, y power type of Q. Okay, and now recall what these both were. These were exactly the Schur functions, right? So this was one of the definitions of the Schur functions. So this here is exactly the Schur function S lambda of x in the infinitely many variables. Okay, so if you wish, think of it as the definition for now. The Schur function in infinitely many variables is just defined to be the sum over all semi-standard Young tableau of x power the type of P. Okay, the fillings can be any numbers from 1, 2, 3 onwards. Infinitely many possibilities there. Okay, so finally what we get, therefore, this is the sum over all partitions lambda partitions S lambda of x, S lambda of y. Okay, so what we have are in some sense three different, so this we'll call as formula 3. This is the third formula for the Cauchy product, 1 minus xi yj inverse. Okay, so I have three different formulas, and these three formulas are all of the same type in some sense. Okay, that the Cauchy product is a sum over all partitions of some polynomials, a family of polynomials u lambda of x times some other family v lambda of y. Okay, and this is sort of the starting point for the definition of an inner product on the space of symmetric functions. So here's the definition of the inner product. Okay, so we say, we could define it in any one of the three ways, but let's follow the standard definition. So we define an inner product on the space of symmetric functions by requiring that, so if I just tell you what values it takes on bases, for example. So I take any pair of partitions lambda mu. So I know that H lambdas form a basis for the space of symmetric functions, M mu's form a basis, and I am telling you what the inner product is between this basis elements H's and the basis elements M's. So I am telling you for each lambda and mu, H lambda with M mu is 1 only if lambda is mu and 0 otherwise. Okay, so and extend linearly or bilinearly. Okay, so in all of this we could assume, since we are also interested in the power sum symmetric functions, that we are talking about the ring of symmetric functions with coefficients in the field Q. Okay, so at this point, we don't know anything more about this inner product. We don't know that it is an inner product, etc. All we know is that on this pair HM, we are defining the value to be delta lambda. Okay, but here's the interesting fact, and where the Cauchy identity also comes into play. So here's a proposition. It says, suppose you are given a family of symmetric functions u lambda and v lambda. Okay, lambda partition of n for all n. Okay, are bases. Say B bases of the space of symmetric functions of degree n. Okay, maybe we should use D for degree. So it takes symmetric functions of degree D for all D at least 1. Okay, so in fact 0 as well. You could just pick, degree 0 is just the constants. So you pick bases of the degree D symmetric functions, okay, for all D. Okay, then the following are equivalent. Okay, the following two statements are equivalent. The inner product, as we just defined, and we don't yet know its inner product, just a pairing, u lambda v mu is delta lambda mu for all partitions lambda mu. Okay, so the inner products between these two families is delta lambda mu is actually equivalent to the following statement, that if you take u lambda of x, v lambda of y, okay, and you do this for a fixed degree essentially. Okay, so since I want to also keep track of degree, I'll just put an additional variable t, and let me just say I'll run this over all partitions. So the product u lambda of x, v lambda of y, t power mod lambda is the same as the Cauchy product. Okay, now I'm also keeping track of degree, so I'm putting another t there. Okay, so 1 minus t xi yj. So I claim that these two are actually equivalent statements. Okay, so observe that this is true for the h's and the v and the m's, right? Because that's how the inner product is defined to start with. That was really our starting point, that h and m are defined to be orthogonal with respect to this, they're sort of dual with respect to this form. That's how the form is defined. And for h and m, of course, we know the Cauchy identity, right? That's exactly this identity here. I mean, with the t's, but that's the same thing. That's the same as matching degree by degree. Okay, so this identity we know in the case of h's and m's. Okay, so there, of course, this statement is true. But what's interesting is that this identity, statement 2 actually implies statement 1. It is a way of checking whether the family U and the family V are duals with respect to this form. Okay, so that's this statement here. So proof I'm going to skip and sort of will put this as maybe one of the problems in the exercises. So it's not too difficult. It's just a simple linear algebraic computation. But let me move ahead to the consequences, which is something we are interested in. So as a corollary to this theorem, we conclude the following, that what was the second version of the identity? It was in terms of power sums, right? So there are two corollaries, that the power sums satisfy the following property: p lambda p mu by z mu. So remember, these are the things which came up. in the second identity, okay, for all partitions. So the power sum symmetric functions are, well, not orthonormal but orthogonal with respect to this form. P lambda is, well, with P lambda by Z lambda, it has inner product 1. Okay, but P lambda P mu is 0 if lambda is not equal to mu. And here's the very important corollary. It says Z lambda with S lambda with S mu is actually delta lambda mu. In other words, the Schur functions form an orthonormal basis with respect to this inner product. Okay, and you can sort of maybe use this 2 here to show that this is an inner product, that it satisfies all the 3 axioms that you require of inner products. For example, the symmetry and so on. Right? If you interchange, you still get the same answer. So all of that will follow from the third axiom, for example, or from that second for that matter. Okay, so that's an important thing, that you can actually define inner products. And the other important statement about inner products. So we actually have, just to summarize what we have so far, we have a set of bases for the ring of symmetric functions, the monomials, the H, the E's, and we talked about the power sums and then the Schur functions. We talked about the involution omega. The involution has the following nice property, that it interchanges H with E. It maps P to itself with a sign. Okay, we still don't know what it does to S. We sort of said it does the following to M. It maps it to another family of symmetric functions called the forgotten symmetric functions. Okay, so this is what omega does. It maps these two to themselves. Okay, P maps to itself with some sign. Okay, H we still don't know. So this is an involution. Sorry, S we still don't know. And now finally what we have also defined is an inner product on this space. Okay, now what does this inner product do? It has the following property, that H and M, right, it sort of has some duality between H and M. So H lambda with M mu is delta lambda mu. Okay, so H and M are somehow taken care of. P and S are taken care of. P is orthonormal with respect to this form. Okay, not orthogonal, and S is orthonormal with respect to the form. So these are the properties that we have proved so far. Okay. Now the other interesting statement here is that this is actually the form that we have defined is in fact omega, or it's invariant under omega. So let's also just see that from this fact. Plain, we can actually use that second to say that the involution, the form is omega invariant. Omega invariant. Form is omega invariant. Okay. Proof, let's just check it on the basis P lambda. So what do we know? Omega P lambda comma omega P mu. So what is omega P lambda? There was an epsilon lambda and an epsilon mu. Okay. Now observe that P lambda P mu is after all 0, right? Unless lambda equals mu. So this is nothing but epsilon lambda square delta lambda mu. Because of course, if lambda is not equal to mu, we don't care. But observe, epsilon lambda square is definitely a 1, because it's after all, epsilon lambda is a plus or a minus 1. So this is just going to be delta lambda mu itself, which is the same as, sorry, there's a z lambda which I missed. Z lambda times this. Okay, and that's the same as the original P lambda P mu. So what this second identity gives you is that the form is in fact omega invariant. Okay, so this is sort of an interesting statement in itself, because going back it says, remember M and H were actually dual with respect to the form, and the form is omega invariant. So it actually says that E and F are dual with respect to the form, okay, just by applying omega to both of them. Okay, great.